What's up, folks? MASH is back, and today we'll be doing the 2022 Paper 1 Chemistry. Today we'll be doing the 2022 Paper 1 for Higher Chemistry. Yeah, only 25 marks, so don't worry too much about this one, especially since it's multi-choice, so you can really just, like, put something completely random if you wanted to. You know, put random letters you don't know. But anyway, we'll get straight into it. I'll stop rambling. An element contains covalent bonding and London dispersion forces. This element could be what? Well, let's go and do the old process of elimination. So boron, we can eliminate. It's a covalent network. So it would just contain covalent bonding. There will be no London dispersion forces. So yeah, we can get rid of that. Next up, for the opposite reason, we have neon. We have to eliminate that because it's a monoatomic element. It's a noble gas. It doesn't bond with anything else. It only has London dispersion forces. So, say monoatomic here. Sodium. Sodium is a metal, so metallic bonding with itself. So yeah, it wouldn't have any London dispersion forces. All the metals would kind of be connected together. So I'll say metal. So at least it has to be sulfur, which, I mean, maybe it doesn't click in your head that it would be a covalent bond, but sulfur is actually special. It actually forms S8 groups. It's S8 molecules, so it's not diatomic. It forms this molecule of 8 sulfur atoms, which has covalent bonding. All the sulfur atoms are bonded like a ring, but also these rings of sulfur, they also connect to other ones via LDF. So yes, it would be D. The graph below shows the relative quantities of energy equivalent to successive ionization energies for an element. The most stable ion formed from an atom of this element has a charge of what? Okay, so stable, that means that we want the some lower energies, right? We don't want anything weird. And how we can tell from this graph what the stable ion would be formed is the energy difference here, right? So this is a massive jump. This means that the third electron must be happening from an inner shell, which means the atom would be will only have 2 electrons in its outer shell. So its most stable ion would be, if you remove those 2 electrons, which would be 2+. I don't really want to save this, do I? There we go. So it'd be A. Hydrochloric acid, HCl, has a higher boiling point than just plain hydrogen. Because, well, why? Polar covalent bonds are stronger than the covalent bonds in H2. This is technically true. Well, actually, no, not really. It's not really true at all. And also, polar covalent bonds do not affect boiling point. They would affect, I believe, yeah, they would affect a boiling point or melting point. Anything. I guess maybe plasmination point, but no. So polar covalent bonds are stronger in than the van der Waals forces in H2. This is technically correct, but it doesn't matter because we're not comparing the same thing here. Of course, the intermolecular, like the covalent bonds, are going to be stronger than van der Waals forces, but it doesn't matter because when you boil something, remember, I'm being dancing around the point a bit. If you're doing this with a discrete covalent molecular substance, then you're breaking the intermolecular forces of the van der Waals forces between the molecules. So we go down once more. So this one's garbage because you're comparing 2 different things. C, on the other hand, van der Waals forces in HCl are stronger than van der Waals forces in H. That is true, and it does cause the higher boiling point because basically HCl is able to use PD-PD interactions rather than which are stronger than normal LDF, which is only accessible by hydrogen, because HCl has a different electronegativity between hydrogen and chlorine. Yeah, so van der Waals forces in HCl are stronger, that is correct. But just to double check, we'll see if D is correct. Van der Waals forces in HCl are stronger than covalent bonds in H2. That's false on 2 levels. Van der Waals forces are always weaker than covalent bonds, and this doesn't matter because covalent bonds do not matter for boiling point. So yeah, all of garbage apart from C. Complete the circle. Which line in the table would best describe elements that act as reducing agents? So remember, reducing agents, they want to reduce other molecules. So that means they want to give away electrons. So they want to become oxidized themselves. And remember, oxidation is loss, reduction is gain. So an oil rig, so that means it wants to lose electrons. So we can already get rid of A and C. And then would it be electronegative? Well, electronegative, remember, is the tendency to attract electrons. So it's basically how much you want electrons. And if we, in fact, we look at our data sheet over here, we find that stuff like fluorine, which really likes electrons, a very high electronegativity. If we go up to our, where is it? Probably past it. I swear I'm not very good. If you look at this, all the best oxidation agents down here, because it's base fluorine really like stealing electrons from other people. So yeah, you would want a low electronegativity here. So you want loses electrons and low electronegativity, which would be B. The correct redox equation for reaction of iron 2 ions with acidified dichromite ions is what? Okay, so I have to go through here and make sure everything is balanced. Well, I guess we'll start at the top and see if it all makes sense. So remember, we've got to have all the elements have to be balanced, and charge is probably the main thing. If I'm looking at this correctly, will have to be balanced. So both sides must have the same charge. So on this side here, we've got -2, then 14 plus. That'll be -12. Plus 12, and then we have a 2 plus here, so it'll be plus 14. Sorry. And then on this side though, it's only a +3. So yeah, this doesn't seem correct. Try B. We've got 2 minus here, so that's a minus plus 12 again. So we're on 14, but this time we have 2. Oh, sorry, that would be +6, but whatever. It's the point still stands. +6 does not equal 14. But same thing here. But we do have a +3 iron atom. Which doesn't make any sense because it's reduction of iron 2 ions, which means we'd have to add on electron, like remove electrons, but we want to gain it. So I don't know what B's doing. It's just completely insane. We'll go on to C. We'll keep adding up these charges, see if we eventually get somewhere with these. So it'll be -2 plus 14, so it'll be 12, and then plus 12 here, so we get up to 24. Over here, so that's +6, +7, but then we have +6. So the charge does not match up. So that's unfortunate. So we're left with D. So now with process elimination, we can actually say that D is the correct answer. But let's go and double check it. So we'll go through here. It's 2 minus. It's 12. That'll be 12 plus. Then plus another 12. So it'll be 24. 24 is the magic number. 2 times 3, that is 6. And then 6 times 3, that's 18. 18 plus 6 is 24. So this one is the correct answer. A mixture of magnesium bromide and magnesium sulfate is known to contain 3 moles of magnesium ions and 4 moles of bromine ions. How many moles of sulfate ions are present? So let's go and write out the formulas for both of these. So again, magnesium has a valency of 2, which means and bromine has 1 because it's in the 7th group, and I prove it here. See, bromine's here, so we only have 1 thing. Magnesium will have 2, which means the formula would be MgBr2. And then magnesium sulfate. Sulfate should be a 2 as well, if I remember correctly. Yep, there we go. So it's 2 negative. So magnesium sulfate will be MgSO4. So if we have 3 moles of magnesium ions, they're going to have to be divided up between them. We have 4 moles of bromine ions, but remember we need double the bromine ions for one thing, which means 4 moles. If we have 4 moles of bromine, bromine is diatomic, remember, so bromide ions. So if we have 4 moles of bromide ions, then we have to have 2 moles of magnesium ions, which is all well and good, and then we have to have, that means that we only have 1 magnesium ion left for sulfide ions, which means it's going to have to be 1 to 1 here, right? So that means it'll have to be 6A. So sorry, that was a wee complicated what it says. But anyway, move on to number 7. The correct name for this ester is what? So the way to name esters is we're going to decide which side is the acid, and the side with the The CO with double bonded oxygen is the acid, and then the other one is the alcohol. And now we're going to count up the carbon chain length in both of these. So for the acid, we've got 4 carbons, that'll be butane, and alcohol, we've got 3. And the alcohol would come first. So 3, that's going to be propane. So get rid of these 2. So it'd be propane, and then we know that this one would be, 5, because there's 1, 2, 3, 4, 5. So we get rid of butanate, and it would be propane pentanate. Yeah, I always forget to count this carbon here in the functional group, which is a bit of a sore spot of mine. So remember to count the carbon in the functional group. Right. So, question 8. The structural formula for a compound is shown. We've got this thing here. Which of the following is not an isomer of this compound? Okay, so I'm going to go and actually write up a formula for this. So, well, actually, formula. So we're going to count up all the different types of elements and then see what we get. So 1, 2, 3, 4, 5, 6, 7, 8 carbons. How many hydrogens we have? So we've got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And then finally we have a single oxygen atom. So it'll be C8H16O. So let's have a look around. Octan 410. Remember the molecular general formula for aldehydes, or the ketone, sorry, is would be CN. H2N. O, and you can see, well, 8 times 2 is 16, so this can't be it, because it would be an isomer of this compound. 2-ethyl hexanal, in a similar vein, well, the aldehydes are basically just sort of rearranged ketones, so that'll be the same. And well, ethyl, that's 2, and hex is 6, so you have 8 carbon atoms, so B can't be it either. 2-ethyl hexane 1O. This might work. We've got, but because we've got this double bonded here, if it was just pure alcohol, we'd actually have 2 extra hydrogens. So yeah, this wouldn't be an isomer, so it may actually be our correct answer, but we'll just double check with our D. So methyl, heptyl, so methyl, that's 1, heptyl is 7, so 1 plus 7, that's 7, and it's also a ketone, which means you would have 2 less hydrogens because you've got a double bond somewhere, which means that it's got to be C. Oh, sorry. Gabapentin is a medicine that can be used to relieve nerve pain. Which line of the table shows the 2 functional groups present in this compound? Okay, well, I see quite a lot of amine groups. Got an amine group there. And then over here we have a carboxyl group. Okay, so that means it must be A, because you've got amine and carboxyl. There is no hydroxyl, there's no OH, because, well, there is an OH, but it's part of the carboxyl group. It's connected to a carbon with a double bond of oxygen, so there's no hydroxyls. So cross all of them off, and there's no, I don't believe there's any carbonyls. I guess you could say it's a component, but remember, this is a different functional group than a carbonyl. So yeah, there's no nonsense around here. Anyway, we'll move on. Number 10, purino is a compound that occurs naturally in citrus fruits. Which line of the table correctly describes the reaction of purino with bromine solution and with hot copper 2 oxide? Okay, so bromine solution, this we see if it was a saturated compound or not. Now, is this a saturated compound or not? Well, it isn't. It's unsaturated because you've got this double bond here. We could fill it with bromine atoms, which means we should actually get a reaction with bromine solution. So A and B are out. So then, what about with the reaction with hot copper 2 oxide? So basically, what is this asking is, can we oxidize this? And the truth is we can, because it's an alcohol, you see, with this OH hydroxyl group at the end, which means we can oxidize this into an aldehyde. So you would actually get a brown solid in the reaction. So that means it must be C. 11. The iodine number of an oil is the mass of iodine in grams that will react with 100 grams of oil as a measure of degree of unsaturation. Olive oil has an iodine number of 84 and palm oil has an iodine number of 48. Which of the following statements is correct? Okay, so iodine is quite similar to bromine, which means you can basically say this is how much this will be basically more of iodine. If you can more iodine, the more unsaturated a molecule is. So use that information. Which one of these statements will be correct? Palm oil is more saturated, and so yeah, believe palm oil would be more saturated, because it's got it takes less stuff to saturate it, right? It takes less iodine, so you can get rid of C and D, but it does have a lower melting point than olive oil, or will it have a higher melting point? Well, if you're more saturated, then you actually have more hydrogens, right? Because if you have less double bonds, you have more hydrogens connecting to your carbon atoms, which means you have more electrons, and therefore stronger LDF, and also your hydrocarbon chains, because normal hydrogen, a saturated arbitrary chain would be like this, it'll be mostly kind of straight, but when you have an unsaturated one, what you do is you get bits where it kind of breaks off and goes in another direction. If you have it nice and straight, then all of them can lie very neatly against each other, which means that you would have more point forces being created between them, and that means you'd have a higher melting point than olive oil. So it's B. 12. The structure of a soapless detergent molecule is given below. We've got this tail section and we've got this ionic head section. Which line in the table describes a step in the cleansing action of a soapless detergent? Okay, so this section here, we can clearly see that it is ionic, so it'd be hydrophilic, right? And then this section here is nonpolar, so it'd be hydrophobic. So we go through here. So head section is hydrophobic. It's not hydrophobic. It's hydrophilic. And it's so that means we've already established that it has to be B just from this alone, because hydrophilic, it literally means likes water, right? So if we know this is hydrophilic, which means it has to dissolve in water. But this should check just the hydrophobic to dissolve in oil. Yeah, because it's non-polar. So it'd be similar to oil, so dissolve in that. So yeah, it would be B. 13, which of the following is a secondary alcohol? So remember, secondary alcohol is when you have your OH group and it's connected to a carbon, which is connected to two other carbons. So if we go through here, let's see if we can find any. So butane 1-ol, that is a primary carbon because it would be on the first carbon, so it would be kind of on the terminal end, right? So it have just be look something like this. So we know that it can't be butane 1-ol. Now butane 2-ol, it could be because, and yeah, it looks like it would be a secondary alcohol because it'd be like if you had your OH group on that side. So D is looking pretty solid so far, but let's go and double check these two. So 2-methylbutane 1-ol, well that's just it's the same as this our previous one, but if we had a methyl group on here, so you'd be that would still be a primary alcohol. This carbon's still connected to 1, and then so yeah, A can't be right. But what about B? Well, B is actually going overkill, because it's like if it's still this this thing here, well, a methyl group, but we're actually connecting it here, which means it's not a primary alcohol. It's not a secondary alcohol. It's a tertiary alcohol, so it can't be that one. So it has to be D. Move on. Compounds below are examples of flavour molecules found in some plants. Got a cucumber flavour here and a vanilla flavour here, ginger flavour and orange flavour. Which line of the table shows the solubilities of these compounds in water and oil? Okay, so when something's water soluble, what that means is that it's actually quite polar. So you'd have it would be quite asymmetric and be quite a few polar bonds. And if it was oil soluble, it would be quite non-polar, so it would be quite symmetric and wouldn't have many bonds. So looking at this, generally, I see that these two here, ginger flavors, have both got quite a few hydroxyl groups. And our hydroxyl groups make it something quite soluble because they can form hydrogen bonds with water and kind of use it to break themselves apart and dissolve. So I'm thinking ginger and vanilla would probably be water soluble, so that means it'd probably be C. And then just checking cucumber or orange. Well, cucumber has got mostly just a hydrocarbon chain with a small double bonded OH, double bonded oxygen at the end, the carbonyl group, which is not that polar. And orange flavor doesn't even contain any oxygen; it's just pure hydrocarbon. So I would think that I think this answer does make sense. The structural formula for a compound is shown. The product of oxidation of this compound is what? So if we're going to oxidize this, what will happen is, I'm going to draw it out actually. We'll actually replace this OH and this hydrogen, and we'll replace it with a double bonded O instead. So the product of oxidation, well, we can actually have a look at it. It would have to be 1, 2, 3, 4, 5. So it would be based off pentan, and it's not on a terminal carbon because we've got this over here, so we can get rid of the aldehydes. And remember, we always do it for the functional group that's lowest, which means it would be 4-methylpentanone 2,1, which would be B. Because you could, this one technically is true, but it's not how we name things, because we always name things with the functional group being the lowest, not the branch chains. So it'd be B. Which of the following describes how to fill a burette with acid and take the initial reading in a titration? Okay, good old titration knowledge. So, rinse a burette with acid, fill to the above scale of acid, drain some of the acids, and read from the top of the meniscus. It's always bottom of the meniscus, so A is correct. Rinse the burette with deionized water, fill to above the scale of acid, drain some acid, and read from the meniscus. You don't want to, if you're filling something with acid, you actually don't want to rinse it with deionized water, you want to rinse it with acid, so it can't be that. Rinse a burette with acid, fill above the scale of acid, then drain some and read from the bottom of the meniscus. That looks good to me. Rinse with deionized water, shouldn't be doing that, and you don't want to read from the top of the meniscus either, so the answer has to be C. Moving on to 17. Tomato juice contains a mixture of terpenes, including lycopene and beta-carotene. Terpenes can be separated using chromatography. Which of the following is the most suitable solvent to separate lycopene and beta-carotene? But if you look at all these other molecules here, water's polar, ethanol's polar, propanoic's polar, but pentane isn't, which means both of these would dissolve into them, and then we could actually use chromatography, so it'd be B. Number 18. The graph shows that the rate of reaction varies with the concentration of reactant. When the concentration of reactant is 0.06 moles, the reaction time is what? So if you look at 0.06 moles, see it's 0.04, but that's the rate of reaction, so don't be tempted to pick that answer. So if we go and put that in here, it's 0.004, and we're going to go and invert it to kind of cancel out this 1 over t, and we'll get our original time, which is 250 seconds. So the answer would be D. Butene reacts with oxygen as shown. 100 cubic centimeters of butene was reacted with excess oxygen. Compared to the total volume of gases before reaction, what would be the total volume of gases after complete reaction? Okay, so let's go and figure this out. So it's reacted with excess oxygen, so that means that we don't need to worry about the amount of oxygen needed, but we have 100 cubic centimeters here, and since it's excess, we're going to be reacting with 600 cubic centimeters because it's 1 to 6 ratio. So that'd be 700 in all, and then we're going to produce 2 gases here, and water in this case is hot enough that it would be a gas, which means it would be 400 and 400, which of course would be 800, 800, and this would only be 700, so it'd be 100 cubic centimeters more. To be A. 20. An aqueous solution, ethanoic acid, forms an equilibrium mixture with its ions. Which of the following solutions, when added to equilibrium mixture, would flavour the forward reaction? I thought that was flavour. Jeez, food in my mind. So what I want is this first reaction to go this way. So how are we going to do that? Well, let's go through it. Well, hydrochloric acid would be bad because hydrochloric acid would be lots of H plus ions, which means they would go up and it would favour the backwards reaction to convert it back. So B is not correct. Down here, this would be bad for the same reason. This is ethanoate, sodium ethanoate, and that would be bad because it would have more of these ethanoate ions, and that would encourage the back reaction. and sodium chloride wouldn't really do anything. It's a salt, and it's not used in here at all, so it wouldn't help at all. So we'll leave them with C. And this, why does sodium chloride help with this at all? That's because sodium hydroxide, sorry, that's an alkali, so it would react with the OH ions, would react with the hydrogen ions, giving us stable water, so it would reduce H plus ions, meaning that the forward reaction is favoured. Right, now we go on to 21. So we've got some values, energy values associated with a chemical reaction as shown in the table. We've got 30 kilojoules per mole for enthalpy of reactants, 110 kilojoules per mole for activation energy of a forward reaction, and then we have 70 kilojoules per mole for activation energy of a reverse reaction. So what does this mean? Well, enthalpy of reactants, that means that the reactants must start on 30, which they all do, so we can't separate out anything yet. Activation energy is 110 kilojoules per mole, which means we need to, this line here would have to be 110 long, but you can see here this one goes to 110, but it's from 30, so it'd only be 80. So that one's garbage. That one is way even shorter than this one. This only goes up to like 80 from 30, so that's only 50. That's 80. And C, that's the same, it's still 80. But D, there we go, so it goes up all the way to 140, so it would be actually 110. And this is double check, 70, so for the reverse reaction, so the distance between these two should be 70. That'll be 110, sorry. So is it, because it goes from 40 to, oh, that's B, sorry, actually, I'm losing my mind here. For D, it goes from what looks to be 70, because it's in between, then to 140, and so that means that this distance here is 70, which is exactly what it says on the table, which means it has to be D. Consider the reaction pathway below. According to Hess's law, the enthalpy value in kilojoules per mole for reaction Z to Y is what? Okay, so Z to Y, we don't actually know this, but if you've ever done vectors in maths, it's very similar to this. What we're going to do is we're going to take an alternative route to get to the same location. So if enthalpy to change W into Z is minus 210 kilojoules per mole, we want to go back the way. And the way we go back the way, it's like a negative vector in maths. So we're going to say that's actually 210 instead of negative 210. But then the other ones, they're all correct direction. So we're just going to add them all up. So we have positive 210 because we flipped that one. Then minus 50 because we're going in the same direction. And then minus 86. And they give us 74. Positive 74. So we're going to go and select B. We'll move on to 23 now. 50 cubic centimeters or 0.100 mole per liter ammonia solution was transferred into a 250 cubic centimeter volumetric flask. The flask was made up to the mark with deionized water. The final concentration in moles per liter of the ammonia solution is what? Okay, so effectively what we have here is we have how many moles do we have to begin with? We have the concentration is 0.1, and then the volume is 0.05 because we're doing this in liters, remember, which means our total amount of moles is 0.05. So then that 0.05 is then spread over a wider area, over 250 cubic centimeters. So N equals CV, same number of moles because we're not adding anything more with this deionized water. We don't know the concentration, but we do know the volume, which is 0.25. So then we're going to go and divide this by 0.25. Which is 0.2. 0.2, I should say. Moles per litre. And that would be A, because it's you're actually going to calculate and I can convert it to scientific form, and that would be 2 times 10 to the power of minus 2. Right, I'll move on. Penultimate question, 24. An experiment involves reacting 0.02 moles of silver ions with ions of a group 7 element to form 2.868 grams of precipitate. Which of the following is the precipitate? Okay, so excuse me, sorry, just let's go and make a mock equation. So we have silver ions, and it looks like it's silver 1, so it's just going to be plus, and then we want ions of some group 7 element, so I'll represent that as we'll represent that as a literal 7. Now 7 elements always will have a negative thing, and then they'll combine them into a silver BAG, one of the AG, sorry. I've got to fix that. I forgot the chemical symbol for silver. Jeez, what am I doing in my life? But yeah, there you go. Silver. So what we need to do here, we want to figure out what would produce 0.2 moles of silver. How would it produce 2.86 grams of precipitate? So if this is 0.02 moles here, we're producing one molecule that would be Ag 7, right? 7 is our standard for a group 7 element, and we'll have 0.02 moles of that. So using this, we can, since we've formed 2.86 grams of precipitate, we can work out its formula mass. So it'll be N equals M over Fm, 0.02. We know what the mass is. This is quite uncommon. I've never done one of these kind of backwards equations before. And then we don't know what the formula mass is though. So I'm going to go and do this. So what we can do here is we can actually swap the 0.02 and Fm around, because that's how fractions work basically. I'll turn off scientific notation. So 2.8686, and then divided by 0.02, and that will give formula mass of 143.4. Now, what we need to go here is go to our data booklet, and we're going to go scroll up to the page where it tells us all the relative null masses and elements, and we know one part of the compound, so we can take it out of the way immediately. And silver Ag is 170.9. So I do that, 107.9. We'll get 35.5, and this should be familiar to anyone who does chemistry, because 35.5 is of course chlorine, which means it would be silver chloride. And finally, 25, a titration experiment was carried out to determine the concentration of vitamin C in orange juice. A sample of the orange juice solution was pipetted into a flask, and 10 cubic centimeters of water was added to dilute the sample. Starch indicator was then added to the flask. The mixture was then titrated in the flask using iodine solution of known concentration. Which line in the table shows the most appropriate apparatus to use when carrying out the procedure? Right, okay, so it's, if you notice, to add water, right, we want to get 10 cubic centimeters. It says that we have to use that, and beakers, using the measurement beakers are not very accurate, but measuring cylinders are slightly above that. So then we just need to figure out, do we use a conical flask or do we use a volumetric flask? So it's no real need to use the volumetric flask, so we probably just want to use the conical flask because there's no known measurements here. We just add 10 cubic centimeters of water to add to the sample. So it would be a, so yeah, a bit of a weird one here. I don't know why, what the SQA are thinking, but if it doesn't mention exact measurements, you probably don't need to use a volumetric flask. It should be a bit of a waste. But thanks very much, folks, for sticking with me all these minutes. Good luck in your chemistry exam if it's coming up. But yeah, message me any questions in the comments, and I'll see you all next time. Mash out.